Hi, welcome to this particular module. In the last two modules what we have seen the introduction to a fab lab or at least a part or equipment or tool inside the fab lab, and then we understood how the silicon can be manufactured from silicon dioxide, a quick process to understand that, followed by the EEG related probes, where we can say that the leads or the electrodes, right. So, there are wet electrodes and there are dry electrodes, and then we understood the anatomy of the brain, right. Now, let us quickly see what kind of other devices including transistor, diodes we can fabricate if we know how to use the microfabrication process, right. And I will be teaching you a part on how to deposit a material, that is on PVD techniques, a bit on CVD techniques which are chemical vapor deposition, and a bit on lithography. So, to understand how can you create different electrodes using the microfabrication technique, right. So, if you see the applications of microfabrication are many, although our focus is on the EEG electrodes or the chips that are related to neuroscience. Let us also understand that what kind of other applications we can use or we can think of if we know how to fabricate the devices. So, if you see the slide, what you can see is a known structure which is your p-n junction diode, right. You know that when you take a diode, right, this is your anode and this is your cathode. You can say K, you can say C, whatever you want, right. So, the anode will be P, cathode will be N, this is p-n junction. How to fabricate a p-n junction diode, right. So, you can see here this is a cross section of a p-n junction diode, and the way to fabricate this particular structure, I will anyway teach you lithography, but right now let me just give you a quick example that you have silicon substrate. If somebody asks you draw the cross section of silicon wafer, you can draw a rectangle like this. The next step would be to grow silicon dioxide. I will explain you, okay, how to grow silicon dioxide, do not worry about it. Silicon dioxide we have grown using a technique called LPCVD. If you want to grow it, okay. If you want to deposit SiO2, then you can use sputtering. You can also go for, if you want to grow, you can also go for PECVD. PECVD is plasma enhanced chemical vapor deposition. LPCVD stands for low pressure chemical vapor deposition, while if you want to, this is for growth process, growing SiO2. SiO2 is silicon dioxide, and you know silicon dioxide is an insulating material, is a insulator, right. Our silicon is semiconductor, right. Now, what we have as a starting process, the substrate is N type silicon, all right. That means a silicon wafer doped with pentavalent impurities. Now, I want to create a P junction inside the N side silicon wafer. So, what can I do? I have to for creating a P junction inside the N type silicon wafer, what I have to do? I have to create a window okay. Why this window is required? Because if I doped P type material, P type impurities, impurities, right. What are p type impurities? P type impurities are example will be boron. So, if I want to diffuse or dope boron inside silicon, boron cannot pass through silicon dioxide. This impurity cannot pass through silicon dioxide. Silicon dioxide works as a mask. Okay. It acts as a mask. Mask for what? Mask to prevent boron to pass through it, and that is why we have to remove silicon dioxide using photolithography. Okay. We will see what is photolithography, do not worry about it right now. So, I have created a window. Now, after creating a window, we will dope boron. If I dope boron, it will create a layer inside the n type silicon, alright. Let us say, let us pattern it like this. So, it looks like dots. Now, what we will do? If you see the schematic here, right, what you can see that you have to then remove the silicon dioxide, because when you dope boron, what will happen, you know, it will be like this, boron will also be here like this, but we do not want boron on the surface, right, we only want boron in the window area, right, this area what we have shown. So, we have to, and this boron at the surface will become boron oxide or boron dioxide. So, this boron oxide and silicon dioxide we have to etch it, right. This silicon dioxide and boron oxide at the layer at the surface of the silicon we have to remove it. So, removing is etching. So, we will use buffer hydrofluoric acid BHF. If I dip this wafer in BHF, what will happen? This boron oxide and silicon dioxide will get etched. The impurities that are doped inside silicon will be boron, outside it will be boron oxide, alright. The next step would be I will grow a silicon dioxide like this, and then I will create a window. I will create a window to take out the contacts. I will create a window to take out the contacts. So, like this, and from the back side like this. P N silicon, metal to take out the contact. Here also I will have metal deposited and pattern to take out the contacts. This is your anode, this is your cathode, right. This is your anode and cathode, you can see here. So, the point that I am making is, if you know the fabrication, then you can create a, you can design a p-n junction diode. Similarly, you can also design several other devices. So, let us see another device. I will not go into detail about this device and how to fabricate it, fabrication will be a separate module. So, if you see this particular device, what we see here, we have a n channel MOSFET. What is MOSFET? Metal oxide semiconductor field effect transistor. Now, what is the substrate here? We are using p type silicon substrate, okay, and we are doping n plus, that means we are doping pentavalent impurities inside the silicon wafer, right, by creating windows like I have shown earlier. We will take this as a separate class where I will be showing you how to design a process flow for creating a MOSFET. However, just here you focus that you can dope n plus type of impurities inside a p type substrate, and then you have a metal connection, which is this black line here, black shadow boxes, right, these black boxes, and you have a source and drain. Similarly, you have a thin silicon dioxide, right. This silicon dioxide is generally grown by dry oxidation process. In oxidation process there are two processes, one is wet oxidation and another one is dry oxidation. There are advantages and disadvantages with wet and dry. Dry oxidation generally gives a excellent quality of silicon dioxide film, and we will use, or generally silicon dioxide is grown using dry oxidation technique. Over that we have a gate, and that again there is a metal, right. So, this gate is one metal end, let us say P1, this channel, right. When you apply a negative with respect to source, gate is the negative with respect to source, what will happen? Gate is positive with respect to source, what will happen? The n type impurities will form a channel. When gate is positive with respect to source, n type impurities are attracted towards the channel, and that is why this will become another plate. You can say plate 1, plate 2, and there is a oxide between two plates. So, if there is a if there are two plates separated by a dielectric or air, it becomes a capacitor, right. So, this forms a capacitor, gate, oxide, and the n channel that is created because of the gate being positive with respect to the source, alright. So, the point that I am making is we can fabricate n channel MOSFET, we can fabricate p channel MOSFET, we can fabricate CMOS, all using the microfabrication techniques. Now, let us see another application of the microfabrication technique. The another application is in the area of heaters, and when we say heater, we are talking about micro heater. Now, what is heater? If you have a resistor, right, and if you heat the resistor by applying a power, then your heat will be I square R, which is your joules heating, right. Now, what will be the resistance of the coil? The resistance of the coil can be measured by or rho L by A, where rho is the resistivity of the material, L will be length of the pattern, and A will be the area. So, here if I know the thickness, if I know the length, I can calculate the resistance of the heater. How to fabricate this micro heater? So, you can see here in the center there is a silicon wafer, right, there is a silicon wafer, and in the silicon wafer there are 12 micro heaters. See here 1, 2, 3, 4, and you have 3 rows or 3 columns and 4 rows, right. So, you have 12 micro heaters fabricated on a 2-inch silicon wafer. So, if I have 4-inch silicon wafer, if I reduce the distance between two patterns, I can fabricate large number of micro heaters on the single substrate. So, how to fabricate this micro heater is very simple. I will teach you in one of the class, alright. So, another application of the microfabrication or lithography technique is to fabricate micro heaters. The metal for the micro heaters can be platinum, can be gold, can be nickel, nichrome, polysilicon, and so on and so forth. Okay. So, this can be several metals that one can use depending on the availability. You need to deposit the metal on the silicon wafer, and if you deposit a metal on a silicon wafer, what will happen? Let us say this is a metal and this is a silicon wafer. Let us say this is platinum. What will happen? This will not form a right way of fabricating, or it is not right step of fabricating micro heater. Why? Because metal and semiconductor will be shorting. So, you have to create a insulating layer between semiconductor and a metal. So, what you can do? You can take silicon wafer, you can grow silicon dioxide, over silicon dioxide you can deposit platinum. So, this will be your silicon dioxide. Okay. Over silicon dioxide you can deposit platinum. Now, this will not short because silicon dioxide is a insulating material. That is why you can see here the color of the wafer is greenish depending on how we have taken the photograph, but mostly it is green, and somewhere here you can see purplish color. This is because of the silicon dioxide deposited on the silicon wafer. Again, like I said, we will see in detail how can we fabricate the micro heaters on the silicon substrate. Let me take another example. So, now if you want to have 2 layers on the same wafer, that means you want to have a micro heater on the silicon substrate, right, on the oxidized silicon substrate. Like I said, we cannot have micro heater directly on silicon, it will short, and then over that what we want? We want an insulating layer like this, and on the insulating layer we want to have interdigitated electrodes. So, you can see here there are 4 interdigitated electrodes, right. So, how can we create this? This is also possible by using lithography technique. So, these are interdigitated electrodes. If you see the from the bottom, this is silicon wafer, then you have a micro heater, the pads of micro heater are here, then over that you have insulating material, over that you have your interdigitated electrodes. We will see how can we fabricate this as well. Let us take another example. We can also fabricate a piezoresistive micro cantilever. What is micro cantilever? Now, let us see, if you see a swimming pool and the diving board of the swimming pool, if some a diver dives from the diving board, what will happen? This will vibrate, right. This vibration, so it is holding at one end, it is open at another end, right, and that is why it will vibrate. This is your cantilever. If you take a ruler and if you hold it on one side, like I am holding like on this one, right, like this, and you press it here, that will be vibrating. So, this becomes a cantilever, this becomes a cantilever, alright. So, micro cantilever is a cantilever fabricated at a micron scale. So, can we fabricate the micro cantilever? Yes. And can we make it piezoresistive? Now, I have brought a word called piezoresistive. What is piezoresistive? Piezoresistive is a property of the material that when you apply a pressure, there is change in resistance. Whilst you also know what is piezoelectric. Piezoelectric is again a property of material, when you apply a pressure, there is change in the voltage, right. Piezoresistive, change in resistance, piezoelectric, change in voltage, electric, right. So, pressure to electric, pressure to resistance, piezoresistive, piezoelectric. Okay. Remember this thing very well. Now, if you want to create a piezoresistive or piezoresistor inside a silicon wafer, we have to dope N type polysilicon with P type boron material in a certain fashion to form a resistor. We will look into that at some point of time. Right now, what you can see on the slide is a piezoresistor. A schematic is shown on the left side. If you see this one, right. This is a optical photograph. These are the process flow to fabricate a piezoresistor, and this is a SEM image, scanning electron microscope, image of a micro cantilever fabricated using microfabrication process. And here this is a SU 8 tip. There is a piezoresistor which is this guy right here, which you cannot see here, right, and this is connected like this. So, it is diffused inside this thin silicon layer. What is the thickness of this piezoresistor? So, the thickness of this cantilever, is 2 micrometer. What is the thickness of SU 8? This is a tip. SU 8 is about 10 micrometers. Now, SU 8 is very light compared to silicon, that is why it is not bending, and of course, we have taken care of the stress measurement, the stress effects by using silicon nitride. We will discuss it separately, and this is created using a technique called DRIE. So, the etching, if you see, let me just delete this one. If you see, except this guy, it is like a board hanging, right. You see there is a trench here, is it. So, this etching is done with the help of deep reactive ion etching technique. Deep reactive ion etching is a dry etching technique. I told you etching are two types, wet etching and dry etching. So, deep reactive ion etching, D stands for deep, DEEP, R stands for reactive, I stands for ion, E stands for etching, all right. Deep reactive ion etching, right. This is a dry etching technique. So, the silicon has been etched using deep reactive ion etching technique. Okay. So, the point is that we can fabricate piezoresistive microcantilever, we can fabricate micro heater, we can fabricate a transistor which is a MOSFET, we can create a diode. Now, let us see what else we can create. We can also create a flexible sensor, flexible micro sensor, and the flexible micro sensor has a strain gauge. We can see here a strain gauge. This strain gauge is fabricated using PEDOT-PSS. PEDOT-PSS is a polymer which is piezoresistive in nature, all right. PEDOT-PSS is the polymer which is piezoresistive in nature, and then over that polymer there are some insulating material, over that there are gold pads, on that there is SU 8 pillar. You do not have to worry about it right now, you just understand that if you know fabrication you can also create flexible sensors as shown here in this particular slide. Now, let us see how where else we can use our fabrication understanding for. You see EG, you have to understand these terms, okay. ECG, EMG, EEG, ECOG. ECG electrocardiogram, right. EMG electromyogram, electrocardiogram heart, myogram muscles, right. Then EEG electroencephalogram, scalp, the brain signals from the scalp. Electrocardiography, ECOG, from the brain, when you open the skull, place the chip on the brain, ECOG. Okay. Now, let us understand ECG, and for ECG, how ECG, what ECG shows? It shows the functioning of our heart. Generally heart pumps evenly, right, 65 to 70 beats per minute. If a person is running, exercising, the heart rate would increase. But just when I am, let us say, let me take my example. If I am right now giving recording this lecture, right, my heartbeat should not increase more than 75-80, because there is no reason for the heartbeat to increase. But if suddenly it starts increasing without any reason, it is called arrhythmia, and arrhythmia is a heart disease. Same way, in one particular case, heart starts beating or pumping unevenly. This uneven beating is because of the misfiring of signals, and this particular case is called atrial fibrillation, all right, atrial fibrillation. So, how to cure this particular heart disease? So, if you see the slide, what it shows is that the first schematic, you can see here, it shows that the heart, of course, we know heart related diseases are increasing day by day because of lot of issues, right. Our lifestyle, food eating habits, the comfort that we get compared to the earlier times, and less of physical exercise. So, heart related diseases are increasing. Recent study shows that these diseases occur in large population of the world, and if untreated would result in life shortening, that we know. Now, let us focus on this particular schematic. It shows you can see the atrium and the ventricles, right, atrium and the ventricles. Now, what it shows that atrial fibrillation is a heart arrhythmia in which abnormal electrical signals begin in the atria of the heart. This is due to abnormal conduction of the electrical signals to the adjacent tissues. So, what happens if that is the case, remodeling of hard tissue, the remodeling, that means hard tissue will get damaged. You can see it is uneven beating, you can see uneven beating, right. Second is due to blood clot, there may be possibility of clot. What is how it is cured? First is right medications, but in some cases right medications does not work, and that is why the treatment is with catheter ablation. Catheter is a tube like you can see here, and this tube is inserted from the groin area all the way to your heart, and once it reaches the heart, right, we can let us say this is the heart and it reaches the heart, then you have to ablate the heart. What is ablation? Ablation is heating. Heating is ablation. Now, what kind of ablation are there? There is a cryoablation, there is RF ablation. RF frequency to hit the heart is called RF ablation technique. Cryo is to use the liquid nitrogen at very liquid nitrogen, so it will freeze the tissue. Both will create in ablation, both will create in a burning of the tissue. So, if the tissue is burnt, it is destroyed, it will stop conducting, as simple as that. Now, if I want to apply RF frequency, that means I have to touch the tissue. Touching of the tissue, that means if I touch, if I apply more force, then the remaining area would be ablated, or the larger area other than what I decide or what is required to ablate would be ablated. If the pressure or force is less, then the area which needs to be ablated will not get ablated completely, right. So, in both the cases what we have seen is we require optimum force to understand whether the ablation is correct or not. That means, at the tip of this tube what you require? You require a force sensor, and this force sensor we can fabricate if we know the micro fabrication process, all right. So, that is the point. Now, if you see, this is a catheterization process, and here you can see, like I said, that the catheter is inserted through the guide wire from the groin area here, and it reaches to the heart chambers, and then the procedure is performed. And the importance of whatever we have discussed is all the way here, which is at the tip of the catheter. So, what is that? You see, this is the maneuvering mechanism. You can maneuver the catheter, you can move the catheter with the help of the maneuvering mechanism. Now, when you maneuver the catheter, this tube will go all the way inside the heart, and this is the tip where you apply the RF frequency to ablate. Within this tip, there is a sensor which will measure the force from the heart tissue. So, there are mask layout, and then how we can fabricate this sensor, all details are there. Let us not worry about those details as of now. When the time comes, I will explain you how to fabricate these sensors. Okay. Now, let us understand another area of fabrication, and that is on the gas sensor side. So, gas sensor is a sensor. Let us say you have a electrode and you have a sensing material over these electrodes, all right. So, here you can measure resistance. This is a sensing material. These are two contact electrodes, right, and what you are measuring? You are measuring resistance. The resistance of the sensor would change depending on the sensing layer that you use. Sensing layer would change the resistance depending on the whether the gas has a oxidation property or a reduction property. Now, what is oxidation and reduction? If the reduction, if the VOC or a gas, so what is VOC? VOC is volatile organic compound, okay, volatile organic compound. So, volatile organic compound are compounds that are volatile in nature at room temperature. For example, ethanol, methanol, acetone, propanol, isopropyl alcohol, kerosene, petrol, diesel, right, these are all VOCs. While some gases that we need to address, so gases are SO2, NO2, CO2, CO, right, these are all gases. So, VOCs and gases. Now, if the VOCs or gases are having reduction property or reducing are reducing of nature, that means that they, when there is a when the VOC comes in contact with the sensing layer, extra electron is created. If it is reducing VOC, if it is reducing REDUCING, okay, and if it is oxidizing VOC, oxidizing gas or VOC, then the electron will be taken away from the sensing layer. So, if reducing gas, electron is donated, if oxidizing gas, electron is taken away. So, if the electron is donated, the conductivity would increase and resistance would decrease. If the electron is taken away, conductivity would decrease and resistance would increase, right. This change in resistance we can measure with the help of this particular sensor. Now, the applications are many, we will discuss if the time permits. Right now, you just see that we have fabricated sensor using two technique. One is called bulk micro machining, second is called surface plus bulk micro machining. All right, bulk micro machining and surface plus bulk micro machining. Now, these are processed to create or fabricate the sensor. Let us go to the next topic. So, before we reach to the next topic, let me finish the module here and let me start the next module, because it is related to understanding the layers within the cortical column. So, we will take as a separate module. Let us finish this particular module right over here. I hope that you understand that the understanding or learning the fabrication would help you to design several sensors, right, and it can be used for several applications. It can be used as a gas sensor, it can be used as a micro heater, it can be used for transistors, it can be used for the force sensing for RF ablation, and many other platforms. It can be used for flexible sensor, right. So, in the next module, what we will look at, we will look at how to create a micro needle that you can place on inside the cortical column and understand the signals generating from the cortical column. All right. So, it is related to brain, right, and that is why we will be discussing that particular topic in the next module. Till then, you take care.